So we now move on to the second talk of this session, Keep Alive Caching for Hawks Process. And this talk will be presented by Sushirdeep Narayana. Please go ahead.
Hello, everyone. I'm Sushirdeep, and I'll be presenting the work on Keep Alive Caching for Hawks process. This work is with Dr. Ian Kash, and this research has mainly applications in serverless computing. So let me start with an introduction on serverless computing. So what is serverless computing? Serverless computing is a cloud computing abstraction where users pay for the usage of the resources. They do not pay for the resources directly. And so the provisioning, reserving, and the configuration of resources are all handled by the cloud provider. Another name given for serverless computing is function as a service. This is because the users basically have to upload their code as functions to the cloud. And these functions get executed whenever they are invoked or say triggered by events such as timers or HTTP protocols. So popular serverless platforms are mainly Amazon's AWS Lambda, Microsoft Azure, Google Cloud Functions. So let us briefly look at the performance in serverless computing. So this diagram illustrates the performances involved in serverless computing. So in order for the functions to execute faster, basically the code, environment, and the libraries should all be present in memory. This is termed as a warm start. This is analogous to a cache hit. And if the function code, environment, and the libraries are not present in memory, the functions gets executed at a slower rate, and this is termed as a cold start, and this is analogous to a cache miss. So one thing you notice here is in order to say get the best performance, the most simple thing you can do is have the code, environment, and libraries be in memory at all times, but this will be highly expensive. So one of the primary challenges for the cloud provider is to design cost-effective policies. And this is more challenging as the users are built for the usage of resources. So the main objective of the cloud provider is to have high performance with low resource costs. And here is a diagram indicating like the cost involved in a cold start. The cost involved in a cold start is like comprises of downloading the code, starting the container, and the bootstrapping runtime. And so we introduce a model of Keep Alive caches, which helps in designing cost-effective policies. So let me move on to an introduction on the model of Keep Alive caches. So in Keep Alive caches, there is a cost associated with the time an object or an item stays in the cache. And this Keep Alive caches are mainly applicable to serverless computing. This is different from a traditional cache where the cache has a fixed cache size. And the main decision in traditional caches is what object do you want to evict when the cache is full. However, in Keep Alive caches, each object is associated with a time policy, and the cache size is not a concern because the applications are in cloud computing. And the main decision in Keep Alive caches is when is it worth to keep an object in the cache? And we answer this question by modeling it as a trade-off problem between the expected time an item is kept in the cache versus the probability of a cache miss. So let me move on to a more formal introduction on Keep Alive caches. So a Keep Alive cache policy consists of two parameters. The first is a pre-warming window, which is the time the policy waits before it brings in an item or say an application image into the cache. And the second parameter is the Keep Alive window, which is the time during which an item or say an application image is kept in the cache. So this keep alive window is active either after the pre-warming window or immediately after the function execution. So a definition of keep alive cache policy is a sequence of keep alive windows during which you move an object or say an application image in and out of the cache. And here is a diagram illustrating a keep alive cache policy. So the main goal of this research is to design optimal keep alive cache policies with theoretical guarantees for serverless computing. So let me illustrate the costs involved in a keep alive cache policy with a simple example of a single window keep alive policy. So here is a diagram illustrating a single window keep alive policy. So a warm start is set to occur if the function gets invoked when the keep alive window is active. So the cost involved for a policy during a warm start is given by the expression CP times the duration during which the keep alive window is active, where CP is the cost for a unit resource per unit time. And a cold start is set to occur if the function gets invoked either during the pre-warming window or after the keep alive window. So there are two cases for a cold start here. And the cost of a policy during the cold start, say if the function gets invoked during the pre-warming window, it's just the cost of a cold start. We denote the cost of a cold start as CCS. And if the function gets invoked after the keep alive window, then the cost for a cold start will be the CP times the length of the keep alive window plus CCS. So when you see these figures, you notice that in order to compute the cost of a policy, you need to know the invocation times of the function. However, the cloud provider does not have access to invocation times of the function, exact invocation times of the function. What the provider has access to is the inter-arrival distributions of the function invocation over the previous arrivals. So with this, we derive an expression for the expected cost of a cache policy. And the expected cost of a cache policy is given by the expression integral 0 to infinity pi times g of x dx plus CCS, where pi is the keep alive window, keep alive cache policy represented as an indicator function. So it's 1 during the sequence of keep alive windows and 0 otherwise. And g of x denotes the instantaneous cost of the policy when the keep alive window is active immediately after the time point x. So now that we have an expression for the expected cost of a cache policy, we can characterize an optimal cost policy. So the optimal cache policy can be characterized using this expression for the expected cost of a cache policy. And in order to characterize the optimal policy, we also make use of what is known as the hazard rate of an arrival process. So the hazard rate is defined as the ratio of the probability distribution by 1 minus the cumulative distribution. And it represents the conditional probability that the arrival process dies in the next instance, given that it has survived up to the time point x. So the theorem characterizing the optimal cache policy is as follows. The points of the sequence of keep alive windows over an inter-arrival for optimal policy are at either 0, infinity, or are solutions to the equation CP minus CCS times lambda of x equal to 0, wherever the sign of the equation changes. So the main takeaway of this theorem is that the optimal cache policy is characterized by the hazard rate of the arrival process. So we look at a simple example of characterization of the optimal policy for a Poisson process. So a Poisson process is an arrival process where the inter-arrival distribution is an exponential distribution with parameter lambda. So the optimal policy for the case of Poisson process consists of two possibilities. So the optimal policy is either an infinite keep alive window if CP by CCS is less than lambda. Here, the expected cost for the policy is CP times the expected inter-arrival length, which is CP times 1 by lambda. And the another possibility of an optimal policy is to have a keep alive window length of 0. This is if CP by CCS is greater than lambda, and the expected cost here is just the cost for the cold start. So let us now move on to the Hawks process. So the Hawks process is a non-Markovian extension of the Poisson process, and its characteristic is that it is self-exciting, meaning that each arrival increases the rate of future arrivals. And we basically study the Hawks process that has an exponential excitation function, meaning that the equation for the hazard rate for the Hawks process is given by lambda naught less sum of alpha times e power minus beta times x minus ti, where ti are previous arrivals. And here is a plot of the hazard rate for the Hawks process. So as you can see, lambda naught denotes the background intensity. Alpha is the sudden jump in the conditional intensity after an arrival, and beta denotes like the exponential decay of the conditional intensity after an arrival. So we apply the characterization of the optimal cache policy for the Hawks process. And we find that the optimal cache policy for the Hawks process is a single window keep alive policy, where the length of the pre-warming window is 0. And the length of the keep alive window has 3 possibilities, depending on the ratio of CP by CCS. So the length of the keep alive window is infinite if CP by CCS is less than lambda of x for all x, or the length of the keep alive window is 0 if CP by CCS is greater than lambda for x equal to 0, or the length of the keep alive window is given by the expression 1 by beta times log alpha plus log of sum of e power beta previous arrival minus the most recent arrival minus log CP by CCS minus lambda naught. Here, the second logarithmic expression, which is log of sum of exponents, represents like the weight of previous arrivals for the optimal keep alive window. One thing you notice when looking at this optimal policy is that it is history dependent, meaning that you have to compute this optimal policy after every arrival. So a more simple and say advantageous policy would be a history independent policy. So in fact, the fixed keep alive window is the most simple history independent policy. So here the policies just have a fixed keep alive window after a function invocation. And in fact, we find that the fixed keep alive window policy is a 2-factor approximation of the optimal keep alive policy. This result follows from the ski rental problem in online algorithms. In fact, the fixed keep alive window policy is also the policy used by popular serverless platforms like Amazon's AWS Lambda and Microsoft Azure. We also design another history independent policy named optimized time to live policy. So this is a history independent policy, but it depends on the process of the Hawks parameters. And the way we compute it is, first we simulate the Hawks process arrivals based on Hawks process parameters. Then we compute the optimal keep alive window lengths on the simulated arrivals. And the optimized TTL window length is assigned as the empirical average of the optimal keep alive windows on the simulated arrivals. So now that we have discussed all the design policies, we evaluate the optimal policy and the optimized TTL policy against the fixed policy on an Azure data set. We use 2 evaluation metrics for evaluating these policies. The first evaluation metric is the average aggregate cold starts. This denotes the average number of cold starts per application. The second evaluation metric is the normalized wasted memory. This is the total wasted memory time normalized with respect to the total wasted memory time of a 10-minute keep alive window. So here is a trade-off curve of the fixed keep alive window policy. The data point on the rightmost of the graph denotes the fixed keep alive window policy for the 5-minute keep alive window. The second rightmost point is the keep alive window policy for the 10-minute keep alive window. So as you notice, as you move to the left of the curve, the length of the fixed keep alive window is increasing. So one thing you notice in this trade-off curve is as you increase the length of the fixed keep alive window, you're decreasing the average number of cold starts. And as the average number of cold starts are decreasing, you're increasing your wasted memory. So this is in fact the trade-off that was talked about in the introduction. Here is a plot of the optimal keep alive policy. So as you notice, the trade-off curve of the optimal keep alive policy, Pareto dominates the trade-off curve of the fixed keep alive policy. And here is a trade-off curve of the optimized TTL policy. The trade-off curve for the optimized TTL policy also suggests that the optimized TTL policy is a very good approximation of the optimal policy. And these performance curves are only for Hawks process applications in the dataset. So we also plot the performance curves for all applications in the dataset. And for applications that are not Hawks process, we apply the corresponding fixed policy. And as you notice, the Pareto domination effect of the optimal policy and the optimized TTL policy is slightly attenuated. This is because around 25% of the applications in the Azure dataset were identified as Hawks process applications. So the remaining 75% of applications had different distributions. So a more complete approach would be to identify the hazard rate of, say, those distributions and apply the optimal policy for according to the hazard rate of those distributions. So in conclusion, we presented a model for keep alive caches that captures the trade-off between cost of keeping objects in the cache versus cost of a cache miss. And the applications of keep alive caches are in serverless computing. We discussed optimal policy and optimized TTL policy in detail for the Hawks process. And we looked at the performance of optimal policy and the optimized TTL policy on the Azure data trace. And we saw that it yields small improvements, but yet meaningful improvements. So thank you.
So I now invite Hongyi Wang to discuss this paper. She will be joining us virtually.
Hi, everyone. Can you hear me, by the way? Can everyone hear me, by the way?
Maybe while we are trying to set it up, if there are any questions from the audience, maybe this is a good time to ask. Yes. Any volunteer can please pass the mic to him. Here. Yeah.
Thank you so much for the excellent talk. I found it super clear. That was awesome. I just wanted to know why in the evaluation metric, why didn't you just also plot the total cost, which seemed to be the objective that you were trying to minimize in the entire talk, and then you moved on to like this kind of like two-dimensional evaluation metric scenario, which I may miss something obvious, but I just didn't understand why you just also gave the total cost essentially of these policies.
Yeah, so So the total cost, you can actually, can be derived as a function of wasted memory. So the cost is CP. So if it's a warm start, the cost is like for the Hawks process, the cost is CP times the inter-arrival length if it's a warm start. So the inter-arrival length is basically the wasted memory during the warm start.
Okay.
CP, you can normalize it to 1. And during the cold start, the cost is CP times the length of the keep alive window plus the cost of the cold start. And the length of the keep alive window is the wasted memory in the cold start. So the cost is basically a function of wasted memory. So the plot would look similar to this. There wouldn't be much of a change.
Okay, I think it's off time, but
Yeah.
thank you very much.
Okay, maybe we can now try bringing Hongi Wang on the screen.
Yeah, thank you so much. Can the audience hear me, by the way?
Yeah.
All right, awesome.
So Hongi,
So
please let me know when you want me to move the slides, okay?
sure, yeah, I only have one slide actually. No need to move the slide. All right. Awesome. I think I can get started. Yeah. So first of all, I want to express that this paper is really really cool paper for me. I personally work on machine learning systems, so I'm kind of like a little bit outside this community. But when I look into this paper, I think it's a very cool paper. It's actually in our field, it's kind of like a classical machine learning for systems paper. So you basically use some machine learning technology to solve system like challenges. So here, the caching scheduling problem, or kind of like a caching policy movement problem, is a very classical problem. So this the application that this paper is trying to tackle for serverless computing, where you basically have two costs. So one is you kind of like keep everything in cache that will cost you too much, or you don't keep anything in the cache, or you need to cold start every time. So that will basically also cost the system to kind of like a pre-booting, reloading, whatever, doing the configuration. So the takeaway of this paper is basically they build basically a model to capture the cost, and then kind of like try to figure out like a policy for the cache, the policy. So basically, then it's characterized in the paper that the hard rate is it's a very important to basically characterize the policy. So they basically look into two special like distribution for the for the kind of like task coming pattern. So basically one per song, and also one for Hawks process. So it's very cool. Like turns out it works very well in the experimental setup, like tested in the paper. So basically, I have very a few kind of like questions. So one is basically it seems like we need to model the cost. That's quite important in systems. So I do wonder, how does that generalize across different cloud providers? Let's say in the Azure or like Amazon Lambda. That's one thing. And more generally, like how does this model like generalize across different applications? And another thing is basically like it seems like a theory like history dependency. It's not necessarily bad, because like when learning from history, the policy can be captured to like predict better maybe for the future patterns. But it seems like it need to be recomputed for policy for the Hawks process. So I wonder if there's a way to both leverage the history and also avoid recomputation. That's all from me, actually.
Yeah, thank you for the discussion. Yeah, these are some nice questions. So I guess we could generalize the performance to a different cloud provider. But in order to do that, you need to have access to Amazon Lambda's data trace. I don't think Amazon Lambda has released any data trace. We use the Microsoft Azure's data trace because they were released by the Microsoft Azure team, and this is the link and the paper cited that releases the data trace for Microsoft Azure's work. So if Amazon Lambda does release their data trace, then yeah, it would be nice to generalize it. Then the second question, yeah, you could model it to hierarchy of caches, but the model does get more complex when you deal with a hierarchy of caches. There are some there are some time to live caches that are used in content delivery networks, but I'm not sure if they use hierarchy or not. Maybe looking at content delivery network caches could give you an idea of how hierarchy would work for like time to live caches in those areas. And yeah, using history, your question on using history to basically get a better analysis but not recompute, that's a good idea. But still, like if you use history, there would be some overhead. That's why we designed the TTL policy, which doesn't use any history, but instead you use the parameters. So you just need, say, some basic information from the user that tells the parameters, and so your overhead reduces if you don't use history.
Yeah, just one quick follow-up is basically maybe right. So maybe the computation overhead can be addressed by some of system optimization technologies. I mean, maybe we should work together. So you can do parallel computing, you can do asynchronous computing, you can initialize a different thread to do some pre-computing, things like that. Yeah, and I just want to say this is a cool work. It can be definitely extended to a system paper actually. I think I'm pretty sure like a lot of people from system community will like this work.
Yeah, there are some systems paper on TTL caches. So yeah, that's a good suggestion.
So thank you, Hongi. So let's thank Sushirdeep and Hongi for this wonderful discussion.